In today's video, we'll learn about torque. When torque is applied to an object, there are three factors that determine the effectiveness of the force when applied to an axis of rotation. The three being the magnitude of the force, the position of the application of the force, and the angle at which the force is applied. When we calculate torque, torque can be calculated by taking the radius from the pivot point to the application of the force, the magnitude of the force, times the sine of theta, which is the angle at which the force is applied. And when we calculate torque, we're left with units of newtons multiplied by meter. When a force is applied perpendicular to an axis of rotation, it will cause it to rotate. Therefore, the greatest force that can be applied is at an angle of 90 degrees or 270 degrees, perpendicular to our radius. When a force is applied away from the axis, or when the force is directed towards the axis, no torque will be experienced by the object. Torque is considered a vector quantity. So if the turning tendency of the force is counterclockwise, we say that the torque will be positive. And if the turning tendency of the force is clockwise, the torque will be negative. So let's see how we can apply torque to our example below. Our example states that a man uses a wrench that is 0.55 meters in length to tighten a bolt and applies a force of 15 newtons at an angle of 35 degrees below the horizontal. What is the torque of the force applied to the bolt? So first, if we summarize the information we're given, we see that our radius is equal to 0.55 meters and that a force of 15 newtons is applied at an angle of 35 degrees below the horizontal. And to solve for our torque, we know the equation for torque is equal to our radius times the magnitude of our force times sine of theta. Since we know radius, the magnitude of our force, and the direction that the force is applied, we can solve for our torque. Our radius is 0.55 meters. We have a force of 15 newtons, and our force is applied at an angle of 35 degrees. When we multiply our values out, we see that the torque that we are left with will be equal to 4.73 newtons multiplied by meters. And since we see that the force is applied at an angle of 35 degrees below the horizontal, it will cause the axis of rotation to rotate in a clockwise direction, meaning that our torque will be negative. We say that the axis of rotation is in mechanical equilibrium when there is a net external force equal to 0, no translational acceleration, a net external torque equal to 0, and no rotational acceleration. So to calculate the net torque, it's the sum of all the torques produced by all the forces. And we see in our figure below that we have three objects that are exerting a force on our lever. When we calculate the net torque, we can make one of the forces our pivot point, which will make that force of that object equal to 0. On our second example, it states that an arm weighs 41.5 newtons. The force of gravity acting on the arm acts through point A. We're asked to determine the magnitude of the tension force in the deltoid muscle and the force exerted by the shoulder on the humerus to hold the arm in the position shown. So if we summarize the information we're given that the force of gravity acting on the arm is equal to 41.5 newtons. Our force of tension is unknown and our force acted on the shoulder is also unknown. But since our shoulder is in equilibrium, we know that the sum of our torques must be equal to 0. So if we sum up our torques, we'll have the torque of the tension acting in a positive direction minus the torque due to gravity acting in the negative direction minus the torque of the shoulder also acting in the negative direction, all equal to 0. We can expand this equation by taking the radius times the force of our tension times sine times theta, subtract the radius of the force of gravity times sine of its angle minus the radius and force of the shoulder multiplied by sine times the angle that it's applied, which is all equal to 0. And so since we know the radiuses of each of our forces, we can rearrange the equation to solve for our force due to tension. And when we do so, our equation will be the force of gravity times sine of theta times its radius divided by sine of theta multiplied by its radius. If we plug in the values we're given, see that the radius from the origin is 0.29 meters times the force of gravity, which was given to us as 41.5 newtons, multiplied by sine of 90 degrees, divided by sine times the angle that the tension force is applied, which is 12 degrees, times the radius from the point of origin, which happens to be 0.08 meters. We see that our force and torque from the shoulder is equal to 0 since we made this the origin. And we calculate this out, we see that the force of tension exerted on the arm will be equal to 724 newtons. To solve for the force exerted by the shoulder on the humerus, we can take the sum of our forces in the x direction. So we know that since it's an equilibrium, our forces will be equal to 0. So if we sum up our forces in the x direction, we have the force exerted by the shoulder in the x direction minus the tension force times cosine of theta equal to 0. And so we see that the force exerted by the shoulder is equal to our tension force, which we calculated to be 724 newtons, times cosine of 12 degrees, which equals a force of 708 newtons. And then we can sum up the forces in the y direction, which is also equal to 0, by knowing that the force exerted by the shoulder in the y direction plus our force of tension in the y direction minus the force of gravity is equal to 0. To solve force exerted by the shoulder in the y direction, we see that we have the force of tension times sine of 12 degrees minus the force of gravity, which was 41.5 newtons. We see that our force in the y direction exerted on the shoulder will be equal to 109 newtons. And to solve for the force exerted by the shoulder on the humerus, we can use Pythagorean's theorem to solve for the force on the shoulder in the x direction squared plus the force acted on the shoulder in the y direction squared. If we plug in the values, we know that the force exerted in the x direction was equal to 708 newtons squared plus the force in the y direction of 109 newtons squared will give us a total force exerted by the shoulder of 716 newtons. We can solve for the direction by taking theta times the inverse tangent times the force in the y direction, which was 109 newtons, divided by the force in the x direction of 708 newtons, will give us an angle of 8.75 degrees below the horizontal.